In this video, we're going to look at two-dimensional motion. Specifically, we'll be talking about projectile motion, and we'll learn the kinematic equations that are used to describe it. Let's start out with a conceptual question. Two balls are released from the same height at the same time. Ball number 1 is dropped, while ball number 2 is shot horizontally at a high speed of 100 meters per second. Which ball hits the ground first? Go ahead, pause the video, and think about that for a minute, and then we'll come back and talk about it. Well, it turns out that the correct answer is that they reach the ground at the same time. And this gives us a little bit of an indication of how we're going to cover what we call projectile motion. Projectile motion is motion where the object is under the influence of gravity, traveling through the air near the surface of the Earth. And when we're talking about projectile motion, we're assuming that we can ignore the effects of air resistance. So gravity is the only force acting on the object. What we see here is that the vertical and the horizontal motions can be treated separately. In other words, for object number 2, even though it's traveling horizontally at a fairly high rate of speed, that doesn't affect the way the object falls vertically. And so the two objects, whether one is just dropped or one is shot horizontally, because they both start out with no initial velocity in the vertical direction, they will both hit the ground at the same time. Let's take a look at another conceptual question. We shoot two cannonballs, identical balls, with the same initial speed. One is shot at an angle of 70 degrees and one is shot at an angle of 20 degrees. Which goes farther horizontally? Why don't you go ahead and pause the video, think about it for a minute, and then come back and we'll discuss it. So it turns out that these two cannonballs will travel the same horizontal distance. Now, the paths that they travel will look quite different. The cannonball that's shot at 70 degrees will go quite high up into the air before coming down and hitting the ground. The cannonball that's shot at 20 degrees will take a much lower trajectory, but it turns out that it will cover that same horizontal distance. We call that the range of a projectile. So the horizontal distance covered is the range of the projectile. And what we'll be able to show over the next few videos is that complementary angles give the same range. And just in case you don't remember, complementary angles are angles that add to 90 degrees. So a 70-degree angle and a 20-degree angle will give the same range. A 50-degree angle and a 40-degree angle will give the same range. And you probably have a sense of this already. 45 degrees gives the maximum range. And we would like to be able to prove all of that mathematically, and we will as we go through the videos. So projectile motion, again, refers to an object that's moving in two dimensions near the surface of the Earth. The key thing here is that we can ignore air resistance. And in that case, the only force that's acting on the object once it's launched in the air is the force of gravity. Because of this, when an object is undergoing projectile motion, such as the cannonball that we looked at on the previous slide, the object is only accelerating in the y direction, and that's just the acceleration due to gravity, negative g, or negative 9.8 meters per second squared. There is no acceleration in the x direction. Let's look at projectile motion in a little bit more detail. When we take our object and we give it some initial velocity, v0, we know from our study of vectors that that velocity vector can be broken into its components. So its component in the x direction, we call that vx0, and its component in the y direction, which we call vy0. Remember that we said that the object is only accelerating in the y direction. In other words, AY is negative 9.8 meters per second squared, and AX is equal to 0. Since there's no acceleration in the x direction, no matter where we look at the object on its path through the air, the x component of the velocity doesn't change. So this component of the velocity in the x direction, Vx, is the same as Vx naught. However, in the y direction, the velocity is decreasing because the object has a negative acceleration. So again, here would be v, vy, and vx. Notice that at the top, vy is equal to 0, and the only velocity that the object has is just the x component of the velocity. Again, if I drew the object when it's over here, vy is now negative, vx is still unchanged, and our total velocity v would look like that. As the object gets right to the ground, right before it hits, we would now have a larger negative vy, but again, vx would be unchanged, and our total velocity would look something like that. If the object is starting and ending at the same height, then this final value for vy is just minus vy naught. So how do we actually go about solving problems with projectile motion? What we do is we use the kinematic equations that we derived back in our one-dimensional motion days. And the one thing that makes this easier is because the acceleration in the x direction is 0, we get to dramatically simplify the x direction equations. If you go back and look at the one-dimensional equations for the x direction and you set a equal to 0, what you come up with is really only two useful equations. That the x component of the velocity never changes, and that the position can be calculated at any time t with this equation. Now, notice that we have to have the components of the velocity. Often in a problem, what you're given is the magnitude and the direction of the initial velocity. This is where we have to use the vector knowledge that we've covered previously. You have to take that magnitude and direction, v naught and theta naught, and first find the components, vy naught and vx naught. Notice that in these equations, the only thing that go in are the components, never v naught, only vx naught or vy naught. Now in the y direction, the kinematic equations look almost identical to when we looked at them for one-dimensional motion. The only thing that's different is we've had to add additional subscripts because we have to distinguish from the x direction, but otherwise they're identical. At the end of a problem, if you want to find the final velocity v and final angle theta, you'll notice to do that, we once again have to use what we know about vectors. We know that the final y component and final x component can be used with the Pythagorean theorem and the inverse tangent to go back to the final magnitude and direction of the velocity. Time to add to your table. One of the things that I've emphasized to you is that even when you're given a formula sheet for an exam, if you don't know what the symbols mean, that formula sheet won't help you. You'll notice that by the time you've covered one- and two-dimensional motion, you've got lots of different symbols to keep track of. So hopefully you've got a table going and you're keeping track of all these variables. So for example, you now might want to add initial x component of velocity and write that as vx naught, and then of course it's still meters per second, and fill in all the other variables that make up these kinematic equations for projectile motion. Let's do an example to see how we use these equations. One of the things that I want you to notice about the equations is the only variable that shows up in both the x direction and the y direction is t, the time. And so time is the go-between between the two components. This problem says a car drives off a 100-meter high cliff at 30 meters per second. How far from the bottom of the cliff will the car land? Just like in one-dimensional motion problems, we always want to draw a picture. And we're going to make this problem a little bit more humane. We'll make this water. We'll let our car and driver survive. I've got the car driving off the cliff. And one of the things you'll notice about this problem, since the car drives straight off the cliff, the initial velocity we're given of 30 meters per second is entirely in the x direction. So in fact, Vx naught is equal to 30 meters per second, and Vy naught is equal to 0. Okay, that's not going to always be true in problems. In fact, generally it won't be. But in this particular problem, we can see that initially the car is only moving in the x direction. Let's identify the other things we know and don't know. In two-dimensional motion problems, I always put the origin at the bottom left, and that allows me to have all the positions be positive. Therefore, the initial position in the x direction is 0, and the initial position in the y direction is simply the height of the cliff, which is 100 meters. Now, what is the car going to do? It's going to follow a parabolic path down, and what we're looking for is what happens when the car gets to the water. Specifically, notice that what we're being asked for is x, the final position in the x direction. We know the final position in the y direction is 0. Notice that we do not know how much time it takes to get to the water. Also, we do not know the final y component of the velocity. Just like in one-dimensional motion, don't assume that it's 0. Okay, so we don't know what it is. We know it's not 0. We do, however, know that the final component of the velocity in the x direction is Vx naught. Remember, no acceleration in the x direction, so the x component of the velocity never changes. Okay, so how do we go about solving this problem? We only have one equation that can help us in the x direction. It's x is equal to x naught plus Vx naught t. Therefore, it's pretty clear that what we're going to have to do first in this problem is to find t. If we can find out how much time this car is in the air, then we can use our one equation in the x direction to solve for how far it goes. Now what you want to do is look for an equation of those y equations that has t in it and only other things that you know. If you go and look at the formulas, you will find that the correct one to use is y is equal to y naught plus Vy naught t minus 1/2 gt squared. Because you'll notice that we know y, we know y naught, we know Vy naught, and the only thing, and of course we know g, the only thing that we don't know in this equation is t. We want to keep using our correct problem solving strategies that we've been developing through the videos. So the first thing I want to do is cross out anything that's equal to 0. So the final height is equal to 0. Also, the initial velocity in the y direction is equal to 0. So that whole middle term goes away. That makes the problem easy, because often when I see this equation, I think I have to use the quadratic formula. But if Vy naught is 0, then I don't have to. Therefore, I get y naught, or I'm going to actually bring this term to the other side. So I get 1/2 gt squared is equal to y naught. Now solving algebraically, again, remember we always want to solve algebraically first. We get t is equal to 2y naught divided by g under the square root. By the way, we know that time can never be negative, so I don't need a plus or minus there, like I would if I were solving for something other than time. Plugging in the values, we have 2 times 100 divided by 9.8, and what we end up with is a time of 4.52 seconds. Once we know how much time the car is in the air, we can now go back to our x direction and solve for how far it goes. So x is equal to x naught plus vx naught t. Initial position is 0, and I can now plug in the values. So vx naught is 30, and t is 4.52, and I find that the car traveled a distance of 136 meters. So that's how far our driver will have to swim to get back to the bottom of the cliff. Let's look at one more example in this video. During a game at Fenway Park, which is where the Red Sox play, a ball is hit at an angle of 45 degrees with a magnitude of 110 feet per second. The ball is 1 foot off the ground when hit. The ball is hit down the left field line where the wall is 315 feet away and is 37 feet high. Will this be a home run? So first of all, if you know nothing about baseball, have no fear. The only thing that you have to know about baseball is if the ball goes over the wall, it's a home run. And if it hits the wall, it's not a home run. Therefore, the physics question we're trying to answer is when the ball has traveled such that it's in line with the wall, is it above the wall or below the top of the wall? That's the physics question we're trying to answer. So let's start laying out what we know and what we don't know. We're given v naught, and v naught is 110 feet per second. We're told that the initial height, y naught, is 1 foot. I'm going to put my origin right here, and so x naught is equal to 0. The wall is 315 feet away, so really what we're trying to do with this question is say when the baseball has traveled a horizontal distance of 315 feet, what is the height? And if the height is greater than 37 feet, it's a home run, and if it's less than 37 feet, it's not. Notice that we don't know how much time it takes the ball to get there. Let's see. So now that we've got that basic information down, there are two things that I want to mention. Notice that this problem is done in feet. We don't have to convert to meters here as long as we know what the acceleration due to gravity is in feet per second squared. And it turns out it's 32 feet per second squared. So now we can proceed without doing any unit conversions. We just have to remember when we plug in for g to put in 32. The first step in any problem where you're given v naught and you're given theta naught, and in this case theta naught is 45 degrees. Remember, always given with respect to the positive x-axis. The first step is always going to be find the components of the initial velocity. Because remember, in the kinematic equations, we never plug in v naught. It's got to be vx naught or vy naught. Let's go ahead and calculate those. This is where we're just using the basic information that we've covered previously on vectors. So if I've got a vector v naught, that makes an angle of theta naught with respect to the horizontal or x-axis. then I should be able to find the components Vx naught and Vy naught. Vx naught is just V naught cosine theta naught, and Vy naught is V naught sine theta naught. Again, make sure that you are in degree mode. And if you're taking calculus concurrently with physics, you'll find you're switching back and forth all the time, because mostly in your calculus course, you're going to want to be in radians. So I have 110 feet per second times the cosine of 45, and 110 times the sine of 45. And we know that sine and cosine are actually the same at 45 degrees, so we get 77.8 feet per second for both of those. Okay, that's step one. Now, if we want to know how high the ball is when it's covered a distance of 315 feet, you may have guessed that the next thing we want to do is figure out how much time it takes for the ball to get to the wall. We have enough information to do that with the x direction. Our x equation is x is equal to x naught plus Vx naught t. And we've set the origin to be where the ball starts in the x direction, so that's 0. Solve algebraically for t. T is x divided by Vx naught, or 315 feet divided by 77.8 feet per second. What I find is it takes the ball 4.05 seconds to travel all the way to the wall. So at that time, it's either above the wall or hitting the wall. Now I want to pick a y equation that has t in it and allows me to solve for the final height. The equation that makes sense to use is y is equal to y naught plus Vy naught t minus 1/2 gt squared. Notice we're already algebraically solved for what we want, which is y, so we can go ahead and plug in our numbers. The initial height was 1 foot. The initial velocity in the y direction was 77.8. And we have 4.05 for t. Then we have to subtract 1/2. Again, for g, we don't put in 9.8. Because we're in feet, we put in 32 feet per second squared. I'll just put that here to emphasize it, although normally I don't write the units in there as I'm plugging in, times 4.05 seconds squared. If you calculate that, what you should find is that it's 54 feet. And therefore, since that's greater than 37 feet, it is a home run. In our next video, we'll continue to talk about two-dimensional motion and do some more practice problems.